Welcome back, folks. Today we'll be talking about graph traversals, primarily DFS and BFS, that is, depth first search and breadth first search. Just a note, this is an excerpt from a live session we had at DSC Banasthali University.
So let's talk about traversals. Now, the traversals which we use a lot are breadth first search and depth first search. Let it be graphs or let it be trees, we use these a lot. Right now, the problem which we face here is it's fine till the time we are doing recursions. Right, we can do recursions pretty well. We all know that, but a lot of times in the interview, what happens is they give us a constraint, and they give us a constraint that would cause a stack overflow exception if we just keep on doing recursions. So we have all learned that we use queues or stacks for BFS and DFS. But point is, I always tend to forget which one to use for what. So there is a neat trick which I keep in mind. That trick is BQ. Right? BQ is BigQuery. BigQuery is basically a database which is used for storing a large amount of data used for big data technologies and data analytics. So BQ, right? Now BQ stands for BigQuery. It also stands for BFS with queues. Right? So that's one of the quirky things which I do just for remembering what to use. So if I have already used queues for a BFS, then what do I do with BFS? The thing which is left, that's stack. Now, it might not be a good idea to remember exactly like this, because we will have to make sure that we know what we are doing, right, and why we are doing it. So let's see why we are doing it, why we are using BFS, and when do we use BFS, right? And do we know that we are using BFS? I'm not sure, right? At most, initially when we actually start coding, we are not sure, right? So finding all connected components. So connected components, like I mentioned at the very beginning of graphs, it is used for it is used with disjoint sets. Okay, and finding all nodes within one connected component, again, it is again a BFS, because you would just go inside that particular connected loop. Now, let's just see. I mean, these are a bit complicated examples, and I have picked these examples from Karumanchi. I'm a huge fan of Karumanchi, to be honest. Now, let's just see. When do we want to use BFS, or let's say if we want to use DFS, what is the concept behind it? Right. Let us try to understand how it works, how it actually just works. Now, let us consider a black pen. So let's say we have a graph. Let's just make it like a tree, and an array tree, which is again a graph without any cycles. All right. Let us add levels to them, so it's easier for visualization. This thing can be blue. This thing can be green, and this thing can be yellow. Okay. Wow, this is horrible. All right. So what we do in BFS is we pick a node, we move down, we get all of its vertices or children, whatever you want to call it. We save it and then we pick one children at a time. Okay. Now, what should we use? Stack or a queue? I mean, we know that from BQ it is queue. Let's say you do not remember BQ as well. So let me just name them something. 1, 2, 3, 4, 5, 6. Okay, so now we have named our nodes, so it's good. We push in to our, I don't know whether it's a stack or a queue. I will create a logic and then I'll try to find out whether I have to use a stack or a queue. Okay, so now I take it out and I print it. That's good. I have printed it. Now what I do is I try to get its children. So now it's not there anymore. Its children are 2, 3, and 4. 2, 3, and 4. Interesting. So now, if I use a stack, what would happen is I would pick it from here, right? And then I will have to get its children. We do not have it. Let's say what if we have, right? Let's say what if we have. Now we get its children, we add them, right? So we take 4, then we add some x and y right here, and then we print x and y. Doesn't sound to be a breadth thing, right? So I think stacks would not work here. All right, we did not memorize anything. We just tried to do a dry run and we realized that it is certainly not a stack and it is most certainly a queue. All right, so now I take out 2 and I have 5 and 6. I add it to my queue. Since queue 2 is no more, I remove it. Now the next is 3. I get its children. I don't have any. I remove 3, then 4, then 5, and then 6. Ooh, that's good, right? So if you notice that we did not have to memorize whether we should be using a stack or a queue. Right? We just tested our method. We just tested our algorithm. And we found out that it is most certainly a queue. It is not a stack. The same fundamental can be implemented with DFS as well. So if I use the same example, in DFS I should reach the last point, and I have to make sure that I reach the last point first, rather than reaching the breadth of it. All right, so what do we use there? Do we use a stack or a queue? Well, I don't know yet. So we have a stack, we have a queue. We put 1 here. And I have to move deep in this. So I take it out, I print my 1. The next thing which I want to print here is 2. All right, so I take my children, it's 2, then it's 3, it's 4. Okay, now 1 is not anymore in here. I go to 4. Does 4 have any children? No, I print 4. Does 3 have an I'll remove 4. Then I go to 3. Does 3 have any children? No, I print 3 here. Then I go to 2. Does 2 have children? I say yes. So I add those children here, 5 and 6. And then I say that, okay, take out 6 and then we take out 5. Right? So as you have noticed that we have basically gone deep whenever we could. Right? Like for 1 we went till 4 and then we went till 3. And when we reached 2, we went to 5 and 6. Right? So here we just from the very initial part we notice that it is most certainly a stack. It is not a queue. Right?
Alright folks, that's all for today. I hope you liked the video. In the next video, we'll be talking about a problem and how do we approach a problem in Graph. So I'll be picking up a specific problem for LeetCode and we'll try to explain it about how to approach that problem.